So what's important is for like smooth, for right, really a lot of different types of geometries will have the same type of behavior, and that is you have this. And notice before when I drew these in the friction part, I didn't have this part for there. Notice this is a full range of really, really small Reynolds to very, very large Reynolds. So you always get the exact same behavior in all of the shapes, right? They all are going to have this strange sort of thing that goes around. Okay, so this is sort of, right, maybe consider this, right, the super laminar part, right? So sort of right here in the middle, what's happening is right? Remember, for all that boundary layer analysis, we did that non-dimensionalization to actually realize that this has to be met for any of that boundary layer stuff to be true. If it's not, you're in this super viscous range, which is called Stokes flow, which is like dominated by this like really close to this part. So remember, the laminar stuff go actually, right, like laminar in terms of external goes all the way at 10 to the 5. So I think that's like somewhere here. Yeah, it's like somewhere here. Right, this is 10 to the negative 1, that's 10 to the 8. So you get this full range, but really all of the shapes or bodies you look in your book, if you look in your graph, they have this behavior where you have transitional. This is the right super turbulent regime stuff that's happening. So again, sort of right in this regime, we never even talked about that because with all this external stuff, we do the boundary layer analysis. We say like, well, I'm going to have fast flows, airfoils, etc. We don't look at we're not looking at the little marbles dropped in glycerin. That's a Stokes flow problem, which is different. And right, so they're all going to have this situation. There's a scale that you get on your drag coefficient, and then you have something that looks like this. And this is called, some people call it the drag crisis. Why? So roughness in this graph, what does roughness of a ball do, right? That actually moves this part right here, that moves it back further. You get something that looks like this. So this is rough, right? And that's right. This is the aha moment I should give you, where this is why you put dimples in a golf ball, because what you do is you make this separation occur. Right? You make the separation occur later because you trip it at a turbulence sooner. So that's, I don't know. I don't golf, so. But I care more about just the look of this graph, because I just remember it all the time. For any drag thing, you draw some sort of shape, it's still going to look like this, right? It could be like here, and then maybe here, here, right? It's just all of them will have, some of them are super sharp, some of them are super smooth, some you can barely even tell. It's a terrible graph now, but that's the idea. So for external flows, you want to calculate a drag force. You have to look up this coefficient of drag table, especially now. We have no techniques for this undergraduate class to like actually get any of these curves that are happening here. So it's just that process now for drag to go to your drag table, or sometimes even look up what this number is based on the body that you have. And then if you know this number, you can calculate the drag force, and given the drag force, right, you can calculate some things like power, you can calculate energy requirements. I think there's more in the notes, but I think, right, yeah, we're sort of all this external flow stuff that we've done. I hope it just really lets you appreciate like how how real non-dimensionalization of the Navier-Stokes goes about, right? So one thing I wanted to focus on was how to like non-dimensionalize right, sort of walk you through one of them. And the boundary layer is a classic example because you have scales and you get this non-dimensional equations. You use scaling things to tell you something about what matters, right? And right, I kind of wanted to draw the similarities between the external and the the external and the internal. Right, really, I wanted you to get I really wanted you just to learn some of the concepts of boundary layers because they're talked about all the time, and you have to know that they exist. So I really want, I'm just, all of these lectures, I just want you to understand these concepts and realize, right, that this exists, why it exists. We talked about no slip. We talked about that flow looking invested on the outside. So there's some connection that has to happen. And that's what this boundary layer is. For an airplane the size of a credit card, I always remember that for some reason. And then maybe, and then just sort of, and then sort of just to take a step back and just, and just at this point, I just really maybe want to iterate for any sort of calculations that you have to do with this type of stuff. You really should just use the plots for CD and CF based on your geometries. They're in the back of your book, and when it comes to like some sort of force or shear stress you have to calculate, you should just use the plots. Again, I was really, for internal flows, I don't see a reason because you can just calculate those, right, with that explicit Colebrook, or I think it's called something else now. But for the external, right, to really drive you to use these plots and to help you understand. I also wanted you to get used to drawing boundary layer profiles, or just that classical picture, right? So, right, just sort of and how if you unwrap a surface, how it changes, right? I think that's so, right, key to be able to understand those ideas of what's happening. Because that's the idea about this boundary layers. What do you use the boundary layer for? Or like you really use the boundary layer to like understand and conceptualize the physics that are happening around an external flow. For calculations, it's incredibly difficult if we're at this level to use it other way. I mean, like you can get like, right? That's a good equation you can use, and this can tell you how thick the boundary layer is. So you can get problems where you can just calculate the height of your boundary layer, which just involves calculating a Reynolds number using this Blasius solution to like say, okay, it's 5 millimeters. But, you know, I was never satisfied by just like getting to answer that. But maybe you get some satisfaction out of that. Right? We have other relationships, right? And just the idea that these are functions of Reynolds numbers, right? Just like how you had the Darcy friction factors that you calculated before. So it's still the same with these flat plates or things like that. But in the end, you want drag forces, which are composed of the skin friction and the form drag, right? So that's really the biggest thing I want you to remember from this whole external thing is like, you're going to have to start off with external flows is to answer this question of how much power do I need to go that fast in the fluid? Well, you need to know what this force is of the drag force happening on your object, right? Maybe you don't want to measure it before you design it. So then just say to yourself, how would I get that drag force? Well, you now know you have to go to external. You have to use external flow concepts for that. right? You should also remember that to get that, I know there are two parts. I know that there's a skin part and a form part. You should also remember, right, that usually this one is way bigger. Usually. And think where skin friction comes about. Skin friction is the interaction of the fluid around the surface of the body flowing through the fluid. So maybe you had tons and tons of area that this could be really big. But if you're just trying to get off the start, there's nothing wrong with getting to the form drag. Right? And then step before, right? So, right? At least, right, for your book, right, you have to... Right, so if you want to get the form drag, which matters most to you, right, you're going to have to look for these coefficient of drag graphs or tables or your own experiment if you're working somewhere. If it's a pretty specific device, you should probably understand the variables that are going hand, and you could just go, well, do we have a wind tunnel? Do we have some sort of chamber? Let's just make our own graph, and then we can get, right, some statistical reasons of what that number definitely is. And then and then that would be a scale, so then you would ramp things up. That's that law of similitude you must have done term 1, but that's how you would pose those experiments. Other than that, if I think we're going to be done with external flows right now, and then we're going to move on to turbo machinery, which is another calculation heavy part of this entire class. I think I had more in the notes, but you can just read the notes, but I hope, right, that's the idea. I just want you to understand the concepts that happen in this boundary layer. Biggest one being what, right? Right? In terms of boundary layer, that's a big one I think that everyone should remember, right? This idea that this is inversely proportional by a half as well. So that's a big one I want you to remember. Everyone should know that. Right, the exact constants that you get to actually calculate these things, I don't think you'll need to know. It's kind of weird. Okay, I'll just be done.